Ladies and gentlemen, thank you so much for coming today. I'm very happy to be here and share the research conducted by Zijialin, Chen Shan, and Mendelsohn for National Central University. The title of the publication is Automated Arrhythmia Detection Using Hilbert-Huang Transform Based Convolutional Neural Network. This presentation will be divided into 6 parts: Introduction, Related Work, Preliminary, Proposed Scheme, Performance, and we will finally get to the conclusion. Okay, as a start, when it comes to arrhythmia, we have to talk about electrocardiography. In the past, people rely on clinicians to interpret these signals, which may sometimes be misdiagnosed with adverse effects. For this reason, being able to diagnose and classify arrhythmia systematically using machine learning methods is not only convenient and cost-effective. Apparently, relying on machine for the identification of medical conditions in general practice is the future. Here, we propose the utilization of Hilbert-Huang Transform as a method to produce input for convolutional neural network to extract features of arrhythmia and perform classification. The reason why we choose Hilbert-Huang Transform is due to its adaptive and nonlinear properties which can address the complexity of human body properly. Also, to gain an understanding of digital image, we choose convolutional neural network to analyze the visuals produced by Hilbert-Huang Transform. In the past few years, many experts propose similar methods using other mechanisms, such as role-based detection, PCA and Baxter, SVM, STM with adaptive learning rate, and full-layer CNN. While these convolutional machine learning methods produce good results, it requires diligent effort to extract meaningful features capable of differentiating each class. Since each type of arrhythmia has its own morphology, models built using convolution machine learning methods are often patient-specific. Or, to ensure good results, authors have to handpick classes that correspond to handcraft features. Evidently, this is inefficient considering the size and complexity of the data that cannot be easily quantified. As for convolutional neural network related work, which already have a built-in component capable of extracting features without human interference, there are ALEXNet CNN model layer consists of 34 layers utilizing a large data set. Despite outperforming the average cardiologist on sequence and F1 matrix, misclassification occurs in arrhythmia sharing similar morphology. This is because information that are useful for analysis may be lost due to the limitation of raw signals that is two-dimensional in nature. As you can see, improving the automation of feature extracting process and enhancing signal processing techniques is necessary. As I mentioned in the beginning, we use Hilbert-Huang Transform and CNN method in this work. The details of Hilbert-Huang Transform included 2 stages. First, empirical mode decomposition, and second, Hilbert-Huang spectral analysis. The following equation represents the process of empirical mode decomposition. In this step, the original signal will be decomposed into a set intrinsic mode function through a process called shifting. During shifting, an average can be calculated by locating maximum and minimum in the original signal. By subtracting the local average from the original signal, a new signal can be obtained for the next cycle of shifting. The shifting process ends and an intrinsic mode function can be acquired when the new signal meets the requirement. The input signal subtracted by the previous intrinsic mode function will generate signal Rn as the new input signal for shifting. And an empirical mode decomposition terminates when no significant frequency can be extracted from Rn. By using Hilbert-Huang Transform, the most useful information from a frequency band can be extracted for data analysis. Let's now move on to the other essential part of this work, CNN. CNN is a type of deep neural network that proves effective in image recognition and classification. The architecture of a CNN model consists of 3 types of layers: input layer, hidden layer, and output layer. The structure of these hidden layers is a variant of convolutional, pooling, fully connected layers, and an upper layer. In the convolutional layer, features for an image will be extracted into maps. After that, it will be applied with a nonlinear function to preserve non-negative values, and the result will be passing to the pooling layer. What the pooling layer does is to reduce the size and dimension of the feature maps, leaving the most distinguishable features. In the fully connected layer, the previous layer of neuron is connected to the next layer of neurons, and three-dimensional features will be flattened to better produce a scale result for class probabilities prediction. If the error rate for comparing the prediction to the actual result is high, the value of the filter will self-adjust through a series of backpropagation until the model has been optimized. The upper layer then combines the weighted inputs to reduce a scale result. Since data is a vital element for the machine learning algorithm, in our proposed scheme, we decided to get a dataset from a credible and representative website, PhysioNet. The dataset used in this research is taken from PhysioNet Challenge 2017, AF classification for a short single-lead ECG recording, which aims to classify normal sinus rhythm, atrial fibrillation, and alternative rhythm, or noise for a single short ECG record. However, we omit noise class when processing data, as more class is lower, the accuracy of overall performance and noise class itself does not contain useful information regarding arrhythmia detection. Data modeling requires an understanding of the data in order to capture, manage, use, and integrate its essence for practical pursuits. From this perspective, the 2017 challenge dataset contains data relevant to our goal of classifying three unique classes: normal sinus rhythm, atrial fibrillation, and other rhythms. The first class, normal sinus rhythm, is a class indicating good health. On the other hand, atrial fibrillation includes the heart rhythms of those who may eventually succumb to more serious conditions. We can see from the right-hand side picture, the ECG representation of atrial fibrillation is characterized by rapid heart rhythm that is erratic and irregular. Last but not least, we have other rhythms where irregular pattern can also be observed. After knowing data's information, we can get into the deeper part of our system model. Our proposed model contains three parts: preprocessing, Hilbert-Huang Transform, and CNN modeling. In data preprocessing, we follow the recommendation of American College of Cardiology, American Heart Association, and the European Society of Cardiology. We segment original data, which is about 9 to 60 seconds, into 30 seconds. In addition, segments less than a unit requirement we will omit or truncate it. And here's the point. Generally, the denoisance process takes place during data preprocessing. However, Hilbert-Huang Transform is equipped with noise-canceling properties, so we don't have to do this in this step. The way how Hilbert-Huang Transform denoisance is by empirical mode decomposition. Since each mode of intrinsic mode function contains a localized characteristic of given time scale, noise, and unrelated components can be removed from the reconstruction of a signal. In our application, data after empirical mode decomposition yields 13 intrinsic mode functions, as demonstrated in the figure. Due to electrocardiography's variations of power, spectrums being observable in the range of 0 to 20 Hz in the frequency domain, we used a combination of intrinsic mode function modes 2 and 3 to reconstruct a new signal for all three classes. This is the figure after applying the selected intrinsic mode function modes. We can observe that the location of each yellow area corresponding to the R-peaks is a crucial feature in determining heart irregularities. Furthermore, the characteristic of each class become more apparent. Atrial fibrillation and other rhythm classes are denoted by clusters of yellow areas with hints of green, whereas normal classes look evenly spaced with very little to no mix of other colors. Then the image will be further fed into CN to do feature extraction and classification. In the CNN feature extraction part, we use the input layer in which the number of neurons equals to the dimensions of the raw pixel value of the image. Since images are perceived in 3 dimensions, our network will have 3 convolutional layers and corresponding max pooling layers to ensure distinguishable features from low to high are captured. Here, we set our feature extracting filter to 3x3 filter and our max pooling filter to 2x2. In total, we have extracted 32 low-dimensional features, 60 for mid-level features, and 128 high-dimensional features. In the classification part, the fully connected layer will assign a probability of what class the exacted features belong to. Using the softmax operation, the algorithm will then be able to perform multi-classification tests by assigning the probability of a class between 0 and 1 that adds up to 1. As for the output layer, the 3 possible class predictions are normal heartbeat, atrial fibrillation, or other arrhythmia type. In CNN model training, we split our data into the ratio of 3:1 into the training set and testing set. At last, we use confusion matrix and F1 score to verify the performance of our framework. As you can see, normal sinus rhythm in our system is being correctly identified 1,154 out of 1,233 times. Atrial fibrillation is misclassified only 68 out of 375 times. And other rhythm is classified correctly 503 times out of 543. The performance of our model overall using micro F1 yielded 87% accuracy, while macro yielded 86%. The F1 score for each class is 90% for normal sinus rhythm, 87% for atrial fibrillation, and 80% for other rhythm, correlating with confusion matrix. In conclusion, instead of using traditional signal processing technique, we use Hilbert-Huang Transform to decompose a series of signals of the human body into modes containing temporal information for analysis. Also, in order to analyze Hilbert spectrum produced from the transform, we use CNN to automatically extract features of each class for prediction. Since we were able to distinguish normal, atrial fibrillation, and other rhythm with reasonable accuracy, classifying other classes of arrhythmia should be achievable. Thank you so much for coming today. Due to medical reason, the author of this paper is not available to attend this meeting. If you have further questions about this work, please contact the author Minta Sun directly through this email address. Thank you.